Please label these notes Geometric Application 7 notes. These are solids of rotation again, but this time we're going to be using washers. So the first things you need to know is you have to know the area of a washer. And basically a washer is just a circle that has a smaller circle taken out of the inside. So when we're doing the area, we're just starting with the area of the outer circle and then taking away the area of the inner circle. So if the outer circle has radius capital R, pi r squared is the area. Then we're subtracting if the inner circle has a radius little r, pi r squared right here, little r squared. If you want, you can factor out a pi and write it like that. Do not, however, no, you cannot write this capital R minus little r quantity squared. That would be different. We'd have to use the box and we would have some other terms in there, not just these two. So this is as far as you can simplify it. You don't have to, but you can if you want. So the second thing you have to be able to do is to be able to find the volume of a hollow cylinder, so that's really what we're working with this time around. And it's the same idea, area of the base, exact same thing as we did up here, the big radius squared times pi minus the little radius squared times pi, and then times this width or height or whatever you want to call it. So today we're working with volume of solids of rotation. And the second part of that. So let me give you a sample problem and then we'll see what's going on. Find the volume of the solid formed by rotating the area bounded by the line y equals 3x, the x-axis, and the line x equals 1 around the line y equals -1. So first things first, I'm going to draw that out. I'm going to do my axes in pencil because we're going to have a little lines going along here. So here are my axes. I've got one line, y equals 3x. I've got one line on the x-axis, that's y equals 0. One line, x equals 1. And then I've got an axis here at y equals -1. So I'm going to do that nice and dark. There's the axis I'm rotating around. Now notice that the area we're interested in is this area right here. And we're still going to draw a rectangle only inside that area. It's going to be perpendicular to that y axis, it's going to be perpendicular to this axis that we're rotating around. But the thing to notice is that what's happening now is that in the previous problems, this axis was touching the area in question, and now it's not. There's this gap right here. And so I've got another couple little pictures showing you what this looks like here. So what happens is basically that we have two different curves. We take a chunk of it, and we're going to rotate it around like that. But notice right here that this is creating a cross-section that isn't a full circle. It's one of these hollowed out circles that we were working with earlier. It's called a washer. And what that changes is simply that we're going to be using these formulas up here in order to find the area of the cross section rather than the areas that or the formulas for area that we were using earlier. We can do the same thing if we're going around the y-axis. It's also the same idea if we're going around a line y equals or a line x equals, like we are in this problem here. So when I look at what I would get for this sort of a problem, basically I'd get some shape that looks very similar to the one that we saw in the video, where there's this missing part right here, and it forms a washer for the cross section. And so in order to find the area of the base, all I'm going to have to do is use the little formulas up top. So to find the big R, what I'm looking at is I'm just looking at the distance from the axis up to the very tip top function that I'm working with. That's going to be my big R, and then I'm going to take away the piece that's making up the radius in between the axis and the bottom function. So why don't I go ahead and I'll set up the usual parts that we do up here with this. I'm still using this volume from start to stop, area of base times width. But what's changed is that this area of base, I'm going to be using the pi big R squared minus the pi little r squared. Instead of labeling this height, I'm still seeing that this is going to be a dx, so when I'm doing my volume, I can do dx. I can see that since it's x, I'm going to be going here from where x equals 0 up to where x equals 1. But now, what I'm going to do is I'm going to extend this line down to touch the axis. This is going to be my big R. And it's going to equal not the top line minus the bottom line for the purple area, but the top line minus the axis. Notice that these can all be written as f of x, so f of x equals 3x, f of let's call it g of x equals -1 for the axis. So r is simply going to be this top function minus the axis, right like that. Now I'm going to need my little r, so I'm going to go ahead, I'm just going to put this here, that's this distance right here. The radius of the circle that we're going to take out, so we have a hollow cylinder. So little r is still going to be whatever's on top of the rectangle minus whatever's on the bottom, but in this case, let's label this h of x equals 0. Our top function is just 0 minus our bottom one, which is -1. So little r equals +1, big R equals 3x plus 1. Coming back over here, all I'm going to do is I'm going to put it into my formula for area of the base. So I've got pi big R squared, that's 3x plus 1 squared, minus pi little r squared, all of that, times quote-unquote dx. Just as we did before, I can plug this into the calculator. Pi times 3x plus 1 squared minus pi times 1 squared, which is just plain old 1, comma x, comma 0, comma 1. And there we go. So let's go ahead and write down the steps. For this, it's only slightly different than what we've done before. That says steps. First of all, we're going to draw the area and mark a rectangle perpendicular to the axis. Second, we're going to set up our start, stop, and dx or dy. Third, we're going to, and this is the new step, we're going to extend the rectangle to the axis to form big R, and draw a second rectangle for the radius of the circle to take away. So that's the little r. Finally, we'll write the expressions for r and r and set up the answer. So let's take a look at a couple more problems. This is problem 2. Find the volume of the solid created by rotating the area in the first quadrant bounded by y equals x and y equals x squared around the x-axis. Okay, first things first is always to draw the area in question. So just in this first quadrant here, so I've just got y equals x. This one is y equals x squared. We are rotating around the x-axis, so here is our axis. That means we're looking at this area right here. We have to draw a rectangle perpendicular. That means this is going to be a dx, so I can start setting up. We've done this a whole bunch of times, so you might know this already. Oh, let's convert these to f of x and g of x first. F of x, g of x. So that means x equals x squared. 0 equals x squared minus x. We've done this a bunch of times. X minus 1. 0 equals x. 0 equals x equals 1. Those are our two bounds. So we're going from 0 to 1, and our equation we want to find the area of the base. We notice that we're rotating this around this axis, meaning that there's a gap. At least for this part, it narrows down here, but for anywhere there's a gap, that means we have to use this formula. So we want our big radius, which we're just going to extend down. Then we're going to take away the little radius that's right there. And incidentally, if we were going to draw this, what it looked like once we rotated it all the way around, basically what it would look like, here's our axis, here's our shape. It would kind of look something like that if we rotated it. At any rate, our big R right here is going to be this top function, which is x minus the x-axis, which is 0. And this little r is going to be this function right here, which we see as g of x equals x squared minus the axis, which is 0. So when we come to do our equation, we're doing pi big R squared minus pi little r squared. So pi big R squared is just x. minus pi times little r squared x squared squared. And when we put that into the calculator, pi x squared minus pi x squared squared, or x to the fourth, comma x, comma 0, comma 1, 0.419. And there we go. Similar things happen if we're rotating around an axis that is above the area in question. So here's our third problem. Find the volume of the solid created by rotating the area bounded by, and it's going to be the same as we were working with before, y equals x squared, oh, maybe not quite the same, and y equals 2x, around the line y equals 5. Y equals x squared is right there. Y equals 2x. Y equals x squared. But our axis is going to be up here. Y equals 5. So we've still got the same thing. Our area is this piece right here. We're going to draw our rectangle perpendicular, so that means we've got a dx. Actually, I'm not going to put that down there because I'm going to be writing more down there. Let's put that up here. So that means I can start setting up my equation. We definitely have a dx. That means everything needs to be in terms of x. So this is f of x. This is g of x. This is h of x. I can see that my starting point is going to be 0. Once again, we can set these equal to each other. X squared equals 2x. In order to figure out what the bounds are, x squared minus 2x equals 0, x minus 2 equals 0, x equals 0, x equals 2. So that means I'm going from here where x equals 0 up to here where x equals 2. And now area of the base, since what's happening is that I'm rotating this around this axis up here. There's a big gap here. So that means I'm going to have to use pi big R squared minus pi little r squared. And for those of you who like your graphs, I'm just going to do a quick sketch of what this is going to look like. So basically I'm saying we're rotating this area around here. It's basically going to be kind of a curvy sort of cone shape. Okay, so to get my big R, I'm going to extend this to the axis. Now if the axis is above, that's okay. Same idea as if the axis were below. So it actually looks like I really should have written my dx on the other side. I was right the first time. I'll put it over there now just so that it's not in the way. So this one, basically this longer radius, that's going to be my R. Big R is always going to be bigger than little r. So this is capital R. It's going to be the top function, which is 5, minus the bottom function, which is x squared. And then I'm going to take out the circle with the radius little r. And it's okay that this one is touching the top function, whereas in the previous problem, big R touched the top function. Basically, whichever of these lines is longer, that's big R. Whichever of these lines is shorter, that's little r. So little r is also going from 5 on the top. We're going to take away whatever this is. That looks like 2x. So there's my little r. Now I can put that into my equation. Pi big R squared, which is 5 minus x squared squared, minus pi little r squared, 5 minus 2x squared, all of that dx. Once again, fun with calculator. Pi 5 minus x squared squared minus pi 5 minus 2x squared x comma 0 comma 2. Make sure you have 3 places after the decimal for the AP test. And that's pretty much what we're doing. I'd like to show you a couple more just because we can also go sideways with this. So for our fourth problem, we're going to find the volume of a solid created by rotating the area enclosed by y equals the square root of x, y equals x cubed. We're going to rotate that around the y-axis. Okay, square root of x only exists in the first quadrant, so we can limit ourselves to right over there. Y equals x cubed is sort of like this. We are rotating around the y-axis, so that means here we are. And our area is still enclosed right here. So that means we're going to draw our line perpendicular to this blue one, which is up and down. So that means this is going to be a dy, meaning everything here has to be in terms of y. So I'm going to need myself a little bit more room, so I'm going to move this one down a little bit. Y equals square root of x. So let's switch these. Y is going to equal f of y cubed. Take the cubed root of both sides, and the cubed root of y equals f of y. I'm going to sort of box that to show that that's all that one up there. And then let's let this one be g of y, square both sides. And I'm going to box this again so we kind of have that all together. And I can start setting this up. This is a dy function. So that means that I'm going to need y's for my bounds. So as always, we can find the bounds by setting up these two things equal to each other. So cubed root of y equals y squared. It might not be super obvious how to solve that one at first, but I know one thing. I know I really don't like cubed roots for solving. So I'm going to start off just by cubing both sides with that. So y equals y to the sixth. Now let's just get that equal to 0, y to the sixth minus y. Now we can actually factor and solve that one just fine. Factor out a y, y to the 5th minus 1. So 0 equals y, and 0 equals y to the 5th minus 1. Add 1 to both sides. 5th root of 1 is just y equals 1. So those numbers tend to show up a lot just because they're really convenient. So this is my y value, so that goes from 0 to 1. 0 to 1. And then I'm seeing that there's a gap here between this and the axis, so that means that I'm going to have to use the, surprisingly enough, the big R and the little r equation. To find big R, we're always just going to connect our line. If we're going sideways, no worries. Big R, just like we would find anything else, we're going to do the right one minus the left one. Remember, this equation right here is simply the equation x equals 0, or let's see, we've got an f, we've got a g, we've got, let's say, h of y equals 0. So we're going to do this one, which is f of y equals the cubed root of y minus 0. And then for our little r, this is the piece that we're going to take away. So little r equals this one, which is y squared minus 0, or just y squared. So when I go and set that up, that's pi, big R squared is the cubed root of y squared, minus pi, little r is y squared, squared. Fun with calculator. Pi. If you go to math and then 4, it's going to give you the cubed root, alpha y. Make sure that you do another parenthesis and you square that whole thing. And we're going to subtract pi, whoops, that was not it, that's pi. Y squared squared is y to the 4th. Our variable is y. Going from 0 to 1. Make sure I have my parentheses right. Yes, cubed squared. Should be good. .257. Okay, so that's pretty much the idea of it. I do want to show you one more example in terms of what do we do when we aren't rotating around the y-axis, but instead around some other axis, and then we'll be all set. So here's our 5th and last problem. Find the volume of a solid created by rotating the area bounded by y equals 2, y equals 4, x equals 0, and y equals x cubed around the line x equals -1. Okay, I'm going to draw my axes in pencil because there's going to be a whole ton of different lines running around here. So there are my axes. I've got a y equals x cubed, so that goes like that. I've got a line y equals 2. I've got a line y equals 4. got a line x equals 0, and I've got an axis x equals -1. So when you look at this, it's kind of hard to find the area. So we have to look at these black ones. That's why I drew the other axis in pencil, just because we could find it a little bit easier. The area that we're interested in is right here. I'm going to make a nice dark purple line. So make sure you're just being careful and not including anything that isn't supposed to be included here. I do see this blue one here. This is why I do things in multiple colors. I know that this has to be perpendicular, so that means this is a dy. That means everything here should immediately be converted to y's. This is y equals a number. X should be f of y. So I should have a couple f of y's right in here. Let's make this one a g of y. And I know that this one right here should be converted. I'm a little bit short on room, so I'm going to do this over in purple so we can still spot it. So y equals fg, I'm on h of y cubed. So cubed root of y equals h of y. And I'm going to go ahead and box that so I can find it again. There we go. Okay, let's set up what we are already able to handle. So we know that this is a dy. That means we're going from some y value here to some y value here. Conveniently, it's told us what that is. It's y equals 2 to y equals 4. So now we've taken care of these two lines. We can ignore them for the rest of the time. We just have to come up with the formula. So volume, and roll from start to stop, area of base times width. I notice there's a gap between what I've drawn and the axis. That means we're using, surprise, surprise, pi big R squared minus pi little r squared. So I'm going to extend this over here. That's going to give me my big R. So right, which is cubed root of y, minus left, which is -1. And I'm going to draw the other little radius. That's going to be the part that I'm going to take out. On the right, it's 0. On the left, it's -1. So I'm going to subtract -1. Little r just equals 1. Big R is going to be cubed root of 3. Oops, cubed root of y, excuse me, plus 1. Okay, almost done. We just have to put in our little equation here. We are good to go. So we've got pi. Big R is cubed root of y plus 1, quantity squared, minus pi. Little r is 1 squared. That's all in terms of y. And here is the happy little calculator. Pi. Math 4 is going to give me the cubed root. Alpha y is my variable. I'm closing this parenthesis here for the cubed root. Add 1. Now I've got a second parenthesis closed here for the big R. Square that. Minus pi times 1, which is just pi. Alpha y. 2, comma, 4. Okay, that concludes Geometric Application 7 Notes.